Hello students, welcome back. Today we're going to be continuing with Introduction to Functions. So let's recall that a few lessons ago we started the linear equations. So what was the linear equation? Linear equation we learned form of y equal to mx plus b, right, where m is the slope and b is the interception. So we call this a linear function, and essentially we're treating y as a function here. Right, we haven't yet defined what a function means, but in this lesson we are going to be defining it. So we can also write y as y equal to f of x, right, which means function of a variable x. So in this case, x is a variable. All right, and now let's recall the definition. So the definition of a linear equation is the y equal to mx plus b, and it's a slope-intercept form. Right, this is very important because we have different forms of linear equations. So this is one of the equations, slope-intercept form, and the graph of the equation is a line whose slope is m, right, slope which was rise over run, and interception is at point 0, b. Okay, few facts about a slope. Right, a slope is one of the very important parts of the linear equation. So number one, if m is greater than 0, then line rises from left to right. From left to right. And essentially, if we imagine that this is x and y axis, we can have a line going like this. Right, it's raising upwards. Okay, and then 2. If the slope m is less than 0, then line falls from left to right. Okay, and how would that look like? That would look like something like this. Right, when we have x and y axis. And then, okay, if, the third case, if m is equal to 0, line is horizontal, which is the easiest equation of a line, right? Because it is just a simple straight line, which is parallel to the x-axis. And then the last part, part 4, is if the slope m is undefined, meaning that it's something divisible by 0, so we cannot define it, then we can say that line is vertical. And we will talk about this case in a few, of how and why would the slope be undefined. But it would be a straight line. All right, so this is the 4 conditions of the slope that are possible for the linear equation. And let's, of course, remind ourselves how we can have the equation of the line and what is a slope in general. And what is the interception? So recall this drawing right here. We talked about it a few lessons back. And here we have that this part is called rise, this part called run. Here we have a triangle, right? We have a rise and run, and here we have the interception 0, b. Right? This is the equation of a line. Okay, so in this case we can find slope. So it's going to be the ratio between rise over run. So slope is equal to rise divided by run, and that would be equal to y2 minus y1 over x2 minus x1. Right, and so when is slope undefined is when we obviously divide by 0. So m is undefined when x2 is equal to x1. Right, because if they're equal, then we have x2 minus x1, which is equal to 0. And if they are equal to 0, then we cannot find the slope, so the line is going to be vertical. Okay, and now two more. A written definition of it. Right, so the slope m is not of a non-vertical line is this. But if x1 is equal to x2, then we have a vertical line. Okay, and the next type of form that I will discuss is the form of a point slope intercept. So, in order for us to have an equation of a line, we have to have 2 points. But sometimes if we're given, let's say, a slope, we can use just 1 point. So we're going to call it point slope form of a line, right? So that would look like this. So the equation of a line as a with a slope m passing through a point x1, y1 is y minus y1 is equal to m times x minus x1. Okay, and this is called a point slope intersection. And few of the important things about, in general, both forms of it is if we're going to be having multiple lines, right? Some lines can be parallel and some lines can be perpendicular. But what would be the conditions of the lines to be parallel and perpendicular? And this is going to be the conditions. So parallel and perpendicular. Parallel and perpendicular. So here it is for the slopes equations. So two distinct non-vertical lines are parallel if and only if their slopes are equal. Right, that makes sense. We are facing the same direction. We are going at the same angle, so their slopes are equal. So parallel lines means that the slopes are equal. The two non-vertical lines are perpendicular if and only if their slopes are negative, and specifically negative reciprocals of each other. So that is m1 is equal to negative 1 over m2. So, or in other words, we can have it as m1 times n2 is equal to negative 1. So here we have to make sure that neither of the slopes are 0. Right, this is very important because the moment one of the slopes is 0, we have an undefined slope. So in order for those two equations have to be perpendicular, one has to have a slope 0, the other one has to be vertical, right? As an x and y axis case. Okay, and let's go ahead and take a look at one example. So for the specifically parallel and perpendicular lines. So example 1. So we're given an equation y1, which is equal to 2 over 3x minus 5 over 3. We're given a point of 2, negative 1. And we want to find a parallel line through that point, 2, negative 1, and a perpendicular line. Right, so for part A, what are we going to use? We're going to use the point slope formula, right? Point slope form. And we're going to first find the parallel line. Okay, so for parallel line, we're going to have that y2 minus negative 1, right? This is the x value. Keep in mind, this is the x value, this is the y value. So we plug in y value for y, x value for x there. So we're going to have, the slope must be the same, so it should be 2/3 x minus, so the x value, which is 2. All right, perfect. So we're going to have y2 plus 1 is equal to 2/3 x minus 4/3. Now let's go ahead and subtract 1 from both sides. So 1 and 1 cancel out, so we have y2 is equal to 2/3 x minus 7/3. Right, so this is our parallel line. In this case, this is parallel line to our original line. Okay, and now let's go ahead and find perpendicular line. Right, perpendicular, I'm going to use a different color for this. Let's say part B. We're looking for perpendicular line. Okay, for perpendicular line, once again at the same point, 2 comma negative 1, y value. So remember, for perpendicular line, we have to have that m1 times m2 is equal to negative 1. And our equation says that, you know, our slope, y1, is equal to 2/3 x minus 5/3, right? So our slope m1 is actually 2/3. So we're going to have 2/3 times m2 is equal to negative 1. So we're going to go ahead and multiply both sides by the reciprocal of this fraction. Is 3/2 times 3/2, and we will have that m2 is equal to, so negative 1 times 3/2 is negative 3/2. Okay, so now let's go ahead and plug that in. So we're going to have, we will have that, let's see, I use y2, so it's going to be y3, right? y3 is minus the value of y, which is negative 1, is equal to negative 3/2 of x minus 2. Okay, so we're going to have y3 plus 1 is equal to negative 3/2 plus 3. So once again, we're going to go ahead and subtract 1 from both sides. 1 minus 1 becomes 0. So our perpendicular equation is going to be y3 is equal to negative 3/2 x plus 2. Okay, so once again, our original equation y1 was 2/3 x minus 5/3. Our parallel equation is y2 is equal to 2/3 x minus 7/3. Right, and here the slopes are equal, so that's why they are parallel. And then the last one is perpendicular. perpendicular equation is y3, which is equal to negative 3 half x plus 2. That equation is perpendicular at the point 2 comma negative 1. Okay, so this essentially, we covered the line equations, right? And yet we haven't thought yet about the function. But before we move on to functions and start thinking about functions and what it actually means and what we actually do to make a function, here would be the general formulas and the general equations that we need for the equation of the line. So the general form of a linear equation of two variables is ax plus by plus c is equal to 0. A vertical line is x equal to a constant. That means this line is vertical. A horizontal line is y equal to a constant. The slope-intercept form, which initially that we've learned, is y equal to mx plus b. And point-slope form is y minus y1 is equal to m times x minus x1 if we're given 1 point. And if we're only given 2 points, then the complete equation would be the 2-point form. So essentially, we have to plug in the formula for the slope, right? So in this case, the slope m is equal to y2 minus y1 over x2 minus x1. Okay? So we would have, for this one, we have 2 points. For this one, we have only 1 point. All right. Now, so what we actually did to develop the functions. So for us to, in order for us to develop the functions, we had on the left side, we have a y variable, or f of x. And on the right side, we had the variable x. Right, but let's go ahead and actually give a more proper definition of a function and what it actually means. So let's go ahead and start this topic of functions. Functions. Okay, so a function, I'm gonna have a definition. A function f from a set A to a set B. So, you know, we learned about sets in the very first lessons, is when we have like a set of numbers, let's say real numbers to real numbers, right, is a relation that assigns to each element x, which is our variable, and it's located in the first set, set A, exactly one element in the set B, which is our element y, right? The set A is the domain. We call it domain. And the set of inputs of the function f, which is the x values, and the set B contains the range, which is the set of outputs, which we call y, right? And what would be an example? So we have y equal to mx plus b. So we have that x belongs to the domain, and every x value corresponds to a y value. So y belongs to the output, which is range, right? This is input. This is output. Okay, and let's take a look at more concrete example here of to visualize what it means to have inputs and outputs and the relationship between functions. So let's go ahead and take a look at this example. So here we are comparing time of the day to the temperature in Celsius, right? So we want to say that, okay, we have the pairs, right? So this part, time of the day, that's our x. The temperature is going to be our y. Okay, and here we can say that A is our domain, right? This is our inputs, and we have input 1, 2, 3, 4, 5, 6 p.m. And our output is essentially 9, so 9, 10, 12, 13, 15. Okay, so what we can write? We can write, you know, the pairs, right? The points. So we have that point 1 corresponds to point 9, point 2 corresponds to point 13, point 3 corresponds to point 15, point 4 corresponds to point 15, point 5 corresponds to point 12, and point 6 corresponds to point 10. Okay, so here the important part is, you know, we have the x as the input, y as the output, right? In this case, the first set of the time of the day is the input, and the temperature is the output. So in each element of A must be matched with an element in B, right? Some elements in B may not be matched with any element in A, which we had here, right? Some of the temperatures. 2 or more elements in A may be matched with the same element in B, but an element in B in the domain cannot be matched with 2 different elements in B. So essentially what it means is that if we have an X value, right, an input, we cannot have 2 completely different outputs, right, at the same time. At the same time, we cannot. It would be only one input, one output. Right? Sure, we can have 2 different inputs and have the same output. That's okay. That's okay for definition of function. But we cannot have we cannot have it as we have one input and have tons of different outputs at the same time. This is not a function. It's not a good function. So how we can also define it is we can define it, of course, verbally, right? Like we did here. Verbally, that is by sentence that describes how input variable is related to the output variable. Numerically, so very often in industries and in engineering and in other sciences, numerical way is by table. So essentially, you would have a table of data, and you would have to connect the data from the inputs to the outputs and analyze it and understand what each relation mean. And as well as you would have to graph it by points. So, for example, one of the softwares that is very known is Excel. Essentially, you can have input points and the output points, and you can make graphs in Excel. Right? So it would graphically represent the equations. And the way that we are interested the most out of all of this for the algebra classes is, of course, algebraic way of the two variable equations. So let's take a look at a domain, right? Let's actually have more solid understanding of what the domain is and how we can use the domain. So example of the domain of a function. So let me go ahead and say first example. Example 1. So we want to find the domain of f of x of 1 over x squared minus 4. Right, so for that function, we know we're not allowed to divide by 0. So x squared minus 4 must not be equal to 0. But let's find out what values will give us the 0. So x squared minus 4 is equal to 0. Remember, last lesson we did some problems on such polynomials. So we know that it's going to be x plus 2 times x minus 2. Is equal to 0. So we have two solutions, either x equal to -2 or x equal to 2. So that means this implies that x cannot be equal to 2 or -2. Okay, so what would be our domain here? Our domain would be negative. Oh, actually, I'm going to use an equal sign here. The domain is going to be -infinity to -2, right? Then we would have to unite it, right, with the union, which we learned previously. So we unite the intervals. So it's going to be from -2 to 2, right? The reason why we do that is that -2 is not a part of this. We're never allowed to be equal to negative. And then 2 is also not included, so we would have to unite this again and go from 2 to infinity, right? Positive infinity in this case. Okay, so essentially that would be the domain of that function. Now, of course, there might be an implied domains, right? Sometimes in some problems, you might not be even told the domain, but you would have to already know it because, as an example, f of x is equal to square root of x. Right, we learned it a few lessons back that even powers, so even fractional powers, we cannot take a square root of a negative number, right? And we can actually rewrite square root of x as x to the power of 1/2, right? So this kind of problem would require us to know an implied domain. Right, what does that mean by implied? That means that we remember the algebraic rules for square roots of x, right? That wherever is under the square root can never be less than 0. So that means that x must be greater or equal to 0, and that would be an implied domain, right? So if we had something like f of x is equal to square root of 2x minus 1, right? We would have to say, well, 2x minus 1 must be greater or equal to 0, and that's our previous lesson of inequality, so we can add 1 to both sides. We're going to have 2x is greater or equal to 1. Then we would be dividing by 2 on both sides. So we would have x to be greater or equal to 1/2. Right, and that would be our domain. So domain would be 1/2 is included, and then positive infinity. Right, that's what we would have as a domain. And we would not break up the interval because everything before 1/2 is not a part of our domain. Okay, so to summarize our small introduction to the functions, because in upcoming lessons we're going to be talking about more on the combination of functions and the library of all of the functions that we got and transformation functions, and we're going to be even learning later on this course, new functions that you probably have not yet seen, but maybe heard of. So let's have a small recap here. So once again, a function is the relation between two variables such that each value of independent variable corresponds to exactly one value of the dependent variable. So we have a function notation that we learned, y is equal to f of x. We've been using it. We have domain, which is a function of set of values of inputs, and the range is a function of set of values of outputs. And implied domain is the defined by algebraic expression, and the domain is not specified because it's implied that we know some algebraic rules and we know how to properly use them to actually have the domain. Right? That will be it for this lesson, and I'll see you guys next lesson. Thank you.